So in the previous lecture video, we had discussed the power spectral density of binary ASK and binary PSK, and also that led us to identifying what is the bandwidth efficiency or spectral efficiency of those two binary digital modulation schemes. And unfortunately, I made a mistake there when I equated one summation with a summation of impulses. I have promptly identified it there, and I have put a note there that I have made a mistake. So would like to just tell you again to please take note of that. And as I said in that note, fortunately it does not alter the bandwidth efficiency results which we got at in that lecture. Now moving on with the next binary modulation scheme, we take the case of binary FSK. Now for binary FSK, the calculation of bandwidth is somewhat lengthy as well as tricky. So what we will do is I will outline the steps. I will not go to each and every detail, but I will clearly tell you what is to be done. So all the laborious work you will have to do, I will give you clear steps how to do them, because there are some stages where you have to calculate the Fourier transform and Fourier transform of time signals which we don't commonly encounter, so to say. Okay, anyhow, you will know as we proceed through the discussion. Now in binary FSK, we know that the signals are, in the type of binary FSK that we have been discussing so far, the signals are this and this. And of course, for a duration of TB is the bit duration. Now delta F is the frequency deviation. This is the one which differentiates between the two signals, and one of these signals stand for one of the binary digits, that is bit, and the other one for the other bit. And delta F is delta F, in case to ensure orthogonality, delta F has to be an integer times 1 by TB, and in the subsequent discussion we will take delta F as equal to 1 by TB. Remember this, I may not be able to recall this every time. Delta F is taken as 1 by TB in the subsequent discussion. Now what we see is this can be expressed as this can be expressed as 2 pi fc plus delta f by 2 minus delta f by 2. It may look like a useless exercise, but it's going to help us a lot when we proceed with the derivation of the spectral power spectrum as well as the bandwidth efficiency. And this can be expressed as, again, may look like a trivial thing to do, but as I said, it's going to help us. Now when we compare the two, we see that there is effectively a center frequency which is fc plus delta f by 2, and this deviates by delta f by 2 in the negative side from that center frequency, and this deviates by delta f by 2 on the positive side from that center frequency of fc plus delta f by 2. And now we can write s naught t as equal to, we can expand this and write it as, you can use cos A plus cos B, and you can take this as A and this as B to get cos 2 pi fc plus delta f by 2t, that is cos A into cos B, that will be 2 pi delta f by 2t plus root of 2EB by TB sin 2 pi fc plus delta f by 2t into sine 2 pi delta f by 2t. And similarly, S1t can be expressed as root of 2EB by TB cos 2 pi fc plus delta f by 2t into cos 2 pi delta f by 2t minus, so we are taking this as the first term and this is the second term, minus root 2EB by TB sine 2 pi fc plus delta f by 2t into sine 2 pi delta f by 2t. Now we see that this part of the two signals, remember these are still two different signals, this part of the two signals remain the same in the sense what actually differentiates the two signals is this numerical sign. So this part of the signal remains, so irrespective of which bit, and remember these are mapped onto some bits, binary bits, so to say. There are two bits, of course. Say for example this is mapped onto bit 0, this is to bit 1. So we can see that bit 0 and bit 1 is differentiated only by this numerical sign, which means that irrespective of which of the two signals are transmitted, and remember one of these two signals are transmitted, one of these two will be always there on the line. So irrespective of which of these two signals are transmitted, this part will be there always. So if you think I am first sending S0T, then S1, then again S0, 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 S1, random, some random sequence if you imagine, even then you see that this part will be there throughout, which means that when you calculate the power spectral density of the binary FSK signal, this part will be there always, which means that effectively you will have a sine wave cos 2 pi fc plus delta ft multiplied by another sine wave which is cos 2 pi delta f by 2t. This will be there throughout, and this part alone can be expressed as, remember I am going to concentrate only on this now, this part alone can be expressed as root of 2 EB by TB cos 2 pi FC plus delta ft, that is cos A cos B is cos A plus B plus cos A minus B divided by 2 cos 2 pi FCT, the whole divided by 2 that will become, and that makes this as EB by 2B under root. So that's what happens to the part that is not changing with the bits. So now we can say that irrespective of whether S0T or S1T is transmitted and one of these two is transmitted, the sum of these two sine waves will be always there on the line. So one part of the power spectral density is composed of this, and it is nothing but sum of two continuous sine waves. So the power spectral density contribution from this can be easily identified. It will be qualitatively an impulse centered at Fc plus delta F and minus Fc minus delta F, and then you will have an impulse centered at Fc and minus Fc, and the strength of those impulses will be EB by 8 TB each. So I am writing now the power spectral density of only this part, which is there throughout, irrespective of which signal is transmitted. This one we will do later. That is where we have the so-called complications, in the sense you have plus and minus differentiating the signals, whereas this is the same throughout. So it is simply having two cosine waves which are added, one of frequency Fc plus delta F, other one frequency Fc, and each of them the individual RMS, individual mean square power you can calculate, and based on that I can write the power spectrum of only this part as equal to This is the one which is centered at Fc plus delta F and minus Fc minus delta F, two impulses, plus EB by 8 TB, delta F minus Fc plus delta F plus Fc, the two impulses, one at Fc, the other one at minus Fc. So this part is done. So this part we will keep aside. I will clean the board now. This part will be there with us. We have to add this later when we calculate the contribution to the power spectral density from this part. And this part we have the numerical sign changing, so it will be slightly more involved, the calculation. This was straightforward because it was just the sum of two sine waves. And as you know, a sine wave has a power spectrum which is an impulse. And the strength of the impulse you have to calculate based on the mean square power of the sine wave, which is quite obvious here. And it's quite elementary calculation. So such calculations I will not do. Now we have to concentrate on this part. So I will retain only this part on the board. So effectively one signal is this. I will not write S0 T as equal to that because that will be wrong. S0 T is the sum of this and this. So I'll just retain those two signals. I'll just retain those two over there. In fact, they are the ones which really carry the bits. Now what we do is we will take PT, the basic pulse, as equal to sine 2 pi Fc plus delta F by 2t into sine 2 pi delta F by 2t, and AK will be, and I have explained these terms earlier, AK will be root 2 EB by TV. AK will be this, and of course plus or minus depending on which. So in a way it is a simple sort of bipolar modulation, so to say. So plus or minus this is getting multiplied with this. So basic pulse shape is this. So what we need to have with us is, and you know the expression for power spectrum, e power minus j 2 pi Fn Tv, and n is minus to plus infinity. You know this expression which I had, and all these terms I have explained what are they. Yeah. So now what we do is, and remember this is the contribution, this is the power spectrum contribution from this. The previous one we have to add at the end. And now what we do is we will calculate P of f. Once we have P of f, we are almost done. Of course, RAN is easy because it is the same as what it was in the case of binary PSK. Now, if we calculate P of f, we are done. So, to calculate P of f, we see that the Fourier transform of sine pi delta f t, 2 cancels, Fourier transform of this with delta f as 1 by tb. With delta f as 1 by tb, the Fourier transform of this is equal to, please calculate and verify any mistakes, you can bring it to my notice, cos pi f tb e power minus j pi f tb divided by 2 pi tb 1 by 4 tb square minus f square. And Remember, this P of t is defined in the interval 0 to Tb. So you calculate the Fourier transform, you get it like this. Fourier transform of this part alone. Now, if we use the property that, so I will not work out the Fourier transform, that's the job for you. If we use this property that ft has a Fourier transform ff and ft e power plus or minus j 2 pi fct, this is a property, we'll have a Fourier transform which is f of small f minus or plus fc. If you use this property, it is possible to arrive at the Fourier transform of p of t. So what we have here is only the transform of this, and that's getting multiplied by this. So you can write it in its exponential form and use this property, and you will get p of f. So if you do that, you will get p of f. I will not write the expression for p of f. Instead, I will straight away write what will be pf square by tb. I'll straight away write what will be pf square by tb, and that will be equal to 8 eb by 4 pi square cos square pi f plus fc plus 1 by 2 tb into tb plus cos square pi f minus fc minus 1 by 2 tb into tb. This will be divided by 4 f plus fc plus 1 by 2 tb whole square into tb square minus 1, and that whole to the power 2, and this will be divided by 4 f minus fc minus 1 by 2 tb square tb square minus 1 whole square. This will be the result, and remember that I just have to make a small correction here. Remember that the power spectrum is pf square by tb multiplied by n minus to infinity plus infinity ran and all those terms. And since ak is equal to plus or minus root 2 eb by tb with equal probability, ak is a discrete random variable taking on these two values with equal probability. Since that is the case, we note that RA0 is 2 eb by tb, and RAN for all other values of n not equal to 0 will be 0. This is how it was in binary PSK. It remains so here as well. So that gives us the power spectral density of this part as equal to pf square magnitude pf square tb into 2 eb by tb, because only n0 term is relevant. All other terms are 0 because RAN is 0 for n not equal to 0. and it is this that we have here and not pf square by tb. So I should say that pf square magnitude by tb into 2eb by tb is this. Please verify this is equal to this. This is square, this is 2eb into 2eb into 2eb is this. Please verify that. Yeah, so this is the power spectrum of this part. So the final power spectrum of binary FSK will be the sum of this and the 4 impulses that we had earlier. So I would say power spectrum of FSK is equal to this plus EB by 8 TB impulse center at FC plus delta F plus impulse at minus FC minus delta F plus impulse at Fc plus impulse at Fc minus plus impulse at minus Fc. This is the power spectrum, and we will, and remember this is for delta F 1 by TB. So maybe to avoid unnecessary confusion, I will write 1 by TB. Please derive the entire thing. I have given you the steps. 1 or 2 Fourier transforms I have not calculated, and some here and there alterations I have not shown how it is done, but I have told you exactly what is to be done. So this is the power spectrum, and we will plot this now quickly, and that will give us an idea of the spectral efficiency. In fact, that will tell us how to arrive at the spectral efficiency. In fact, this is going to give us an idea of the bandwidth, and then spectral efficiency follows from the bandwidth. This is the frequency axis. We have impulses. I will not worry about the magnitudes. We have impulses. One at Fc. Maybe I'll write here Fc and Fc plus delta F. So there is one impulse at Fc, which is this. Strength is this. I will not mention it because what we are really bothered with is the bandwidth. The other one is Fc plus delta F. That will be Fc plus 1 by TB, because delta F we have taken as 1 by TB. So Fc plus 1 by TB will be this. This is at Fc plus 1 by TB, equal strength. Don't worry about the magnitude scales. And then of course we'll have minus Fc and minus Fc minus 1 by TB. I will not replicate it here. You have to do it if you're noting it down. And then so this is taken care of, one side of it. And now we move on to this. We see that this is going to be there on the positive f-axis, and this is going to be there on the negative f-axis. Now I will again concentrate only on this part. Forget about this, because this is the one which is going to give us the bandwidth. It's the f width that we are concerned with. Now if you see, when you put f is equal to Fc plus 1 by 2 TB, which is at the center here, if you put f as equal to this value, that is Fc plus 1 by 2 TB, you can see that the result of this is going to be 1. Put f as equal to Fc plus 1 by 2 TB, this whole term becomes 0. This is minus 1 square, anyhow it is 1. And cos square pi 0 into TB you will get, and that is nothing but 1. So this is the value of f fc plus 1 by 2 TB, where this is going to peak. I'm not going to worry about the vertical scale, and it's going to drop. You can see it's going to drop on either sides. And when fc is when f is equal to fc plus 2 by TB, you can substitute. If f is equal to fc plus 2 by TB, you can see that the numerator becomes 0. And again, when f is equal to fc minus 1 by TB, the numerator becomes 0. So fc plus 2 TB. When f is equal to fc plus 2 by TB, you can substitute fc plus 2 by fc gets cancelled. 2 by TB minus 1 by 2 TB. That will be 2 minus half. That will be 1.5. And of course, TB and this denominator TB gets cancelled. So it is 1.5 pi. That is 3 by 2 pi. And cos 3 by 2 pi is 0. Cos 3 by 2 pi is 0. So we can see that you will get the 0 here. And when f is equal to fc minus 1 by TB, so this will be 1 by TB. Again, don't worry much about the scales. You can draw a scaled version later if you are very particular about that. And when f is equal to fc minus 1 by TB, you can see that you will get cos pi by 2 in the numerator. F is equal to fc minus 1 by fc gets cancelled, and you will get minus, rather you will get, if I substitute, let me verify it instead of making guesswork, fc minus 1 by TB minus fc minus 1 by 2 TB. So if I put fs equal to fc minus 1 by TB, this is what happens, and I will get minus 3 by 2 into 1 by TB, because 0.5 and 1 gives 1.5. Minus 3 by 2 TB, minus 3 by 2 1 by TB is again, you will get the result as 0 when you substitute here. So the next 0 comes here. There onwards, what happens is, even if this has an oscillatory nature, the denominator, since its magnitude is increasing with f this way or that way, you can see that we can ignore the remaining part, and that will lead us to an estimate of the bandwidth. The bandwidth is fc plus 2 by TB minus fc minus 1 by TB, and that gives the bandwidth as 3 by TB. 3 by TB is the bandwidth. And of course, same thing would have repeated here. I will not draw that. It's just a waste of time. It's just a reflection. So we got the bandwidth now, and remember, all this is for delta f 1 by TB. And once we have the bandwidth, we can straight away say that the bandwidth efficiency or the spectral efficiency is bit rate divided by bandwidth, which is equal to 1 by 3, say 33%, 33.33%. And you can see that this is inferior to the bandwidth efficiency of binary ASK as well as binary PSK. Both of them had a bandwidth efficiency of 50%. So it's inferior here. And performance wise, as we saw earlier, in fact, if you increase delta F further by 2 by TB, the bandwidth efficiency will come down, because when you increase delta F, this bandwidth is going to increase. So binary FSK, unfortunately, when you look at it from the spectral efficiency viewpoint, is inferior to binary ASK as well as binary PSK. Error performance wise, binary FSK performs the same way as a binary ASK, but has a 3 dB inferior performance compared to binary PSK. So this is a quick comparison between these three binary modulation schemes.